Alright, this is going to hopefully be a relatively quick video. This is number 6 in my Yocto series. Thanks for sticking around through all of this. There are a couple of things I want to accomplish. I want to tie together the Linux that we've got working on the board to a broader internet service, just to kind of show, now that we have an operating system, we can start to treat this as custom hardware kind of like any other device or any other machine. What I want to do is I want to add a layer called NTP, the Network Time Protocol, and I'm also going to use a new program here, an application that I've written to set the time automatically. So take the system time and then set the time on our custom IP. But let's talk about what I've got to do the NTP first. So to get NTP working, what I need to do is I need to find documentation about what is required. And there's this nice little Google search you can do. Let me go back to that. There's this nice little Google search you can do, Yocto layer list, and if I do that search, it'll take me to Open Embedded Layer Index. And this is a list of all the different layers and recipes that are available. And in this case, since I'm looking for a package that's a recipe, and I'm looking for the NTP package, and I find that it's provided by meta networking. And so if I click on the meta networking, it's going to show me what its dependencies are. And anytime that we see that we have to have layers, so I need to have this layer as well as its dependencies, that tells me I need to go back to our build directory. And I'm going to run this OE init build and that puts me into the build directory. And I can then edit the conf file and look at our bblayers.conf. I think we did that in like video -.2 or something like that. I don't know. Anyway, I need to add the layers that I don't have. Well, I didn't have the Python or the networking layer, and so I copy and pasted here and added that. I know that it's part of the Open Embedded layer, and so that's how I know to put it there. If I didn't have those in the directory, I would need to see if I could git clone them, but in this case they're already part of my meta Open Embedded, so we're all good. The next thing I need to do is edit the local conf, and this is where we get to add any recipes that those layers provide. And so I want to include the NTP recipe provided by meta networking, but I also want to include my 7mod recipe, which was that kernel module that we built in the previous one. I know I'm making a forward reference here, but we're also going to include a time app recipe. This is the program that I'm writing, or I'm about to write and walk you through. And once I have that time app program ready to go, then by including it in this core image extra install, when I build a new image, Yocto will include these 3 recipes as well as all the defaults. Okay, so let's go ahead and save that file. Okay, so continuing along. In the previous video we did a kernel application. This time I want to do a user application. And to do that, what I've done is in the meta 7seg layer, I've created a recipe directory for any applications I'm going to create. And I created this time app directory. And every project that's going to be managed by bitbake needs to have instructions that tell bitbake how to build your program and install your program. So kind of like the basic services you'd expect to find in any package management or installer system. The configuration file, it must include a license, so that the way these systems work is if you are deploying applications, you need to be able to show like the history of what licenses are present in the system. And so you get to pick whatever license you want to use. I'm using the copyleft, the GNU copyleft license. There's a handful of other ones that are common, or you can even use a proprietary one, but understand that a proprietary one doesn't get you off the hook of your open source licenses, but that's a whole different discussion. We have a summary, we have the checksum for the file, and so for example, in my files directory, is this copying file, and if I do an MD5 sum on the file's copying file, there's the file, and then that MD5 sum should match, and sure enough, it does. The next thing that's present is the list of files that are part of the source. We need a make file, we need the C files and .h files, and this special copying file, that's the license file. Whenever we want to compile, essentially what we're going to do is we could either generate one compilation using the bitbake environment variables, CC for the C compiler, C flags for the flags, or in this case what I'm doing is I'm issuing a make. So whenever you want to compile, just make. And then to install, we're going to use the Unix utility called install, and it actually has a man page for install. And the way install works is it installs a file, and you can specify the permissions and the directories and all kinds of things. The bitbake utility uses the S environment variable for your source, and it uses the D environment variable for your destination. So this is the destination of the root directory for the file system you're creating. And so we want to make sure that the destination binary directory is there. In this case it would be the user bin directory, and then the install-m0755 would install this time map program into the root directory user/bin/time app, and it would be read, write, execute to root, and read and execute for everybody else. Okay? So that's what's going on in the top level. If I wanted to, I could add additional source files, I could add other instructions, special instructions in here, but this is really just a simple template. Inside the files directory then I have my make file, and my make file is a typical make file, all time map and clean. And so the last thing we're going to do is take a look at our timemap.c program. And so this is the standard way we're going to build this application. I have the same I/O control commands that we used in the kernel device driver. Really this should have been moved into a .h file. So that they're kept consistent. Everything else is essentially regular C code. I'm going to get the current time, and Unix uses two different structures for this. The first pair uses a time T structure to get the current time from the clock, and then I'm going to use that to get the time in Greenwich Mean Time. And this is going to give me a breakdown of hours, minutes, and seconds. So this time T is in, let's do a man on that, man time, sorry, man-s2 time. This gets me the time in seconds relative to the Unix epoch, which started in 1970 on January 1st. And so it's going to be at this point some relatively large number. So this is the number of seconds that have elapsed since that original Unix time. This struct TM is now going to be hours, minutes, seconds, days, weeks, weekday, month, day, year, the whole thing. I'm really just interested in the hours, minutes, and seconds. The next thing I want to do is I want to set the time, and I want to set the time based on my current device time. So the Z board is going to have a time. Part of that time is coming from the NTP daemon that we just installed. This is going to read the current time, and now this part of the code is going to set it. So the first thing we're going to do is we're going to open our device driver. We're going to do some I/O controls to set the mode, to set the time and colon period. And then to, remember those were done through I/O controls, and then to change the time, if you remember from the previous video when I used the echo command, we just echoed a value to the device. Well, I can't echo here in C language, but I can write a string, and so we're going to formulate the message that we want to send, and then we're going to write those bytes just like we would if we're going to printf to a file. We're going to write those bytes to our device, and we're going to close the file. And then my little program here is going to go through, it's going to open the device, it's going to read the input like I did when I did the cat command. We're going to read everything into the message string, and I'm going to close the device, and I'm going to show what we read back, and I'm going to look for the occurrence of the word time equals, and I know that the time is going to be 5 bytes later, and so I'll just scanf to get the hours, minutes, and seconds that the device actually has, and then we'll get the time, we'll get the current time again from the clock, and I'm going to print the differences. So we're going to print the hour on the board versus the hour on the 7-segment controller versus the hour from NTP, minutes and seconds. We'll sleep for 30 seconds and we'll do it again. The main point that I want to really point out here is, now that we have the logic for managing the device in our device driver, now we're back to manipulating the device driver's interface from C language just like we would anything else. So as far as our application is concerned, we're just reading and writing bytes. The way that we access the device has been abstracted away, and that's a key operating system point. We have created this illusion of a time service in the device driver, and we have this kind of nice intuitive way of interacting with it kind of built into the device driver, and now the user application is separated from that through that device layer. This is the program that's been running, and we see here that the program is reading back the current time. I'm going to restart it, and we see that it read the current time, and then it updates the I/O controls, and it did a read back, and the readback shows what the current time is, and 2:14. There's a 12-hour difference because I'm in 12-hour mode, and the GM time is in 24-hour mode. The minutes are certainly the same, but the seconds are a little bit different. We're going to see that there's a bug that I've got to try to track down somewhere where the seconds are always 30 seconds off, or so it would appear. So it's kind of a strange way that's happening. But that'll be for yet a different day. So once you've got this ready to go, we're done modifying the time app itself. The next thing we're going to want to do is build it. So I can go into the Pokey build directory, and if I do bitbake, I can bitbake just the time app. And if I bitbake just the time app, it compiles it, and what I can do then is I can navigate around the I'll go back in my history a little bit here. Oops, I'm sorry, that's all the way up here. The the kind of packages are created in a work directory, and I found those by just doing a find command. So find from the build directory any file name that is named time app. Now I see that there's some smaller ones, like little package definitions and some directories. So one thing we can do is we can actually add the perm command, and this is going to be able to show us those that have permission that are executable. In other words, they match the permissions that were installed. So what I want to do is, since this is the one that we just created, I want to sudo and cp that file into var lib tftp boot. Remember, that's the holder for all of our tftp commands. And over on the board, I can bring the I can do my tftp-g for get, -r timemap is the remote file, and put in the IP address, and then I can rerun my timemap. So this would allow me to okay, that should have been, oh, that wasn't the right one. That was the debug. I want this one. User bin. This .debug is the set of debug symbols that can be used by GDB to debug the program, but I can't use it for execution. So now if I do my tftp command again, there we go. So there it runs. Now, I would really like to show just the time difference here. So what I'm going to do is I'm going to edit I'm going to edit my timemap program here so that when I'm printing, I want to print the difference between these two. So I'm going to print the absolute value between these two. And basically what I can do now is just rerun this bitbake command. And that will recompile the timemap program. And okay, so I have an error and it says implicit declaration of fabs. And so it'll throw an error, it'll show you the output of make if there's any, but in this case there weren't any problems. So it compiles timemap, and I can go back to my window over here and do that the sudo command to copy, and now I can go back to my terminal program and hit up arrow, transfer it from TFTP back to the board, and rerun it, and I see that there's 24 seconds of difference. And so if we let this thing run, we should see if there's always 24 seconds of difference or whatever the bug may be, so something that we can try to track down. So that's my kind of design methodology. I will modify the file in the recipe. I'll do the bitbake on just that application. I'll use the TFTP server to transfer the file over to the board, run it on the board. Now see there's 36 seconds of difference, and I suspect we're going to see it goes back and forth between 24 and 36 and 24 and 36. Anyway, let's get that out of the way. That's a distraction. But anyway, what I can do is I can just kind of cycle through until I know that everything is ready to go. And once I'm confident that that TFTP program or the timemap program or whatever it is I'm trying to build works, now what I can do is come back to bitbake. And instead of doing the timemap, I can do the core image minimal. And this time what it's going to do is it's going to rebuild the root file system for the board. And so there it goes. So it'll rebuild the root file system, and now I can take the SD card out and I can re-image the SD card with this new root file system. And the timemap and the 7 driver and the NTP file, they'll all be present in that image because that's what I said to do. The last thing I want to just highlight here is there are times when you're building these embedded systems when you want to be able to like automatically launch a program. While we're waiting for this to build, I want to just point out to you that the way the root file system runs is there is this init.d directory, and in this init.d directory are startup scripts. And the startup scripts are going to run, they're going to be called by the Unix init program as the system is coming up. And as it goes through the various run states, we're going to essentially run through this all of the files that are in one of these RC directories. So these RC directories, I believe it's run commands. The different run levels are 0 is startup, 1 is single user, 2 and 3 are 3 is multi-user. Oh boy, there we go. 0 is halt. I'm sorry. 1 is single user, 2 through 5 are multi-user, and run level 6 is reboot. So if I want to have something run, say during boot time, I would pick one of the RC levels, like say RC2 or RC5. That's the last one that runs. And what we see in RC5 are a bunch of directories that are starting, or a bunch of files that are starting with S for start. So when we enter run level 5, we're going to start networking, and then in numerical order we're going to mount any network file systems, and then we're going to start ntpd and syslog, and then we're going to remove the no login command that prevents logins, and then we're going to stop boot logging. So I could add another command in here, like if I go back to the if I show you here the rc5.d, these are all symbolic links back to init.d. If I go back to init.d, let's just cat one of these files. This is a shell script, and when the file is executed, the shell script is executed, we're looking for start and as an argument. And if we're in start mode, we're going to run the thing, and if we're in stop mode, we're going to stop the thing. So for instance, I can do etc init.d urandom stop, and then I can do urandom start, and that would stop and start the dev random service. If I wanted to, I could follow this pattern, and let's say I had a program that had to run, and that was like what the device needed to be. So for instance, if you were writing the cell phone service, your user interface, like when we launched the Android framework, there's a startup script that's going to launch the Android framework. So when it's done and it transfers control over to that Android framework, it happens because init ran that program. So you can do some Googling around, but this is how you would essentially anchor your application to be the one and only program that seems to be running on the machine, even though the rest of the operating system is running behind it. So I hope you found that helpful. This, I believe, will be the last video in this series on Yocto Linux. If I have some time, I'm going to try to put some videos together on using the SDK and using remote debugging, which is a whole other set of topics that's not really related to Yocto specifically, but to debugging embedded systems in general. So good luck. Hope your projects work out for you. Thanks for watching.